Hello, my dear students. How are you all? I hope you are all doing well. Today we are to continue with measurement. We are to continue with measurement of relationship. And when we say measurement of relationship, it's basically a technique that is used to determine whether or not there exists a relationship between two variables. Now, with this, we will be dealing with two main aspects. That's the correlation and the regression. Now let's start with one of the techniques involved, and that's what we call the scatter plot. The scatter plot or diagrams. When we say scatter plot or diagram, it's a diagrammatic way of determining whether a relationship exists between two variables or not. And this is normally done by plotting a pair of values in the Cartesian plane. So as shown in the diagram below. Now let's start with correlation. Correlation is a statistical technique used to describe the degree of the relationship between two variables. And we shouldn't forget that with correlation, both variables are normally classified as what? Random. What do we mean by they are classified as random? That is when none of the variables depend on the other and vice versa. Then we move on to the aspects of correlation. Basically, we have three main aspects of correlation. We have the positive, the negative, and the zero correlation. Now, when we say a correlation is positive, what it means is that the effect of one of the variables tends to an increase in the effect of the other, and vice versa. That the increase in the effect of one variable tends to an increase in the effect of the other variable, and vice versa. Then when we say a correlation is negative, it means an increase in the effect of one variable tends to a decrease in the effect of the other variables. Likewise, a decrease in the effect of one variable will also tend to an increase in the effect of the other. Then we come to zero correlation. That is where there is no correlation at all. That's the two variables involved are no way related. Now let me give an example of positive correlation. So you can see diagrammatically, this diagram shows a positive correlation. That's if you take the random variable y, as y increases, x is expected to also increase. And in this case, the scatter plots are in some kind of ascending order from left to right. Then another diagrammatic way of illustrating negative correlation is as shown here. With this, you see that the plots or the dots are in descendancy from left to right. Now when it is like this, it indicates that when there's an increase in the variable y, it will cause a decrease in the variable x. Hence the negative correlation. Then when we say it has a zero correlation, that one, the dots or the plots are scattered on the graph. So you can see that here you cannot determine any kind of linearity between the variables. Like you can't tell whether the dots are linear or not. They are just scattered. So when it happens like this, practically we say they are nowhere correlated, or they don't have any relationship. Now, having done with the graphical way of determining correlation, we now move on to a numerical way of measuring the correlation. So we move on to coefficient of correlation. Now with the coefficient of correlation, it is a numerical or quantitative way of determining the strength of the relationship between two variables. Now when the relationship or the correlation that exists between the two variables tend to be linear, then the best coefficient of correlation to use is the Pearson product moment correlation coefficient. Pearson's product moment correlation coefficient. This tells us that there are so many types of correlation coefficients depending on the nature of the correlation that exists between, or the nature of the relationship that exists between the two variables. That will tell you the specific coefficient of correlation to use. So first, dealing with the Pearson product moment correlation coefficient, that one is used when the relationship between the two variables is assumed to be linear. And it is normally denoted by small r. Now mathematically, two formulas can be used. One that I normally term as the conceptual formula, that it gives the conceptual formula definition. Then the second formula, which is r equal to n sigma xi yi minus sigma xi yi, all divided by the square root of n sigma x I squared minus sigma xi all squared times times n times sigma yi all squared minus sigma yi all squared. Now, algebraically, these two formulas are identical in that it is the conceptual formula that is used to prove the second formula, which is the easily calculated formula. That we use it for easy calculation sake. Now, the person's product movement correlation coefficient R normally ranges from -1 to 1. Let me say +1 inclusive. Now with this, whenever the correlation coefficient, that's the Pearson product Pearson product movement correlation coefficient is greater than 0, the correlation between the two variables is termed as positive. Then whenever it is equal to 0, we say the correlation between the two variables is, there is no correlation between the two variables. And whenever the correlation coefficient is less than 0, then we say it is a negative correlation coefficient. Now, in terms of strength, the strength of the correlation between the two variables, whenever R is equal to 1, it means we have a perfect positive correlation coefficient. In that case, graphically, you will see all the points lying on a straight line, and it will be in ascendancy from left to right. When R is equal to -1, then we have a perfect negative correlation between the two variables, which graphically all the points will lie on a straight line in descendancy from left to right. Then when R is equal to 0, it simply means there is no correlation between the two variables. Hence, you will see the graph scattered all over on the plane. Now, generally, whenever R, when I say R, I mean Pearson's movement product correlation coefficient. Whenever R is less than 0.4, we say the correlation is weak. Also, when R is greater than -0.4, we also say it is weak. The correlation between the two variables is weak. On the other hand, when R is greater than 0.6, when R is greater than 0.6, or it is less than -0.6, we say the correlation between the two variables is strong. There's a strong correlation between the two variables. Then when the correlation, or when R falls between 0.4 and 0.6, mathematically as indicated. We say or, let me say, or on the other hand, when negative 0.4 is greater than or equal to R, and R is greater than or equal to negative 0.6, then we say the correlation between the two variables is moderate. Now the diagram below shows a perfect positive correlation. Then this diagram too shows a perfect negative correlation. You can see from the diagram that all the points are lying on the straight line, and it is in descendancy from the left to right on the diagram. Now let's move on to some of the basic properties of the Pearson's product movement correlation coefficient. That's R. Let's take the first point. Say the value of R does not depend on which of the two variables under study. The value of R does not depend on which of the two variables or independent. Now let's come to the second property. Say the value of R is independent of the units in which the two variables are measured. What it means is that you can use correlation, the R, that's Pearson's movement product correlation coefficient, to measure the strength of the relationship between two different entities. That's entities of different units. And that's what we mean by, it means the value of R is independent. It does not depend on whether the units are the same or the two variables involved are the same or not. Then 3, the values of R range between -1 and 1, both inclusive. That's mathematically expressed as this. I think I've mentioned this before. Now if you are to follow the subsequent properties, they've all been explained already. So it's left with you to read. Now, as I said earlier, the strength of the relationship between two variables ranges from strong positive to weak negative. Now let's try to solve some examples using the Pearson's movement, the product movement correlation coefficient. Let's say you have been given this example. The immediate data below represent the amount of fertilizer in kilograms applied to equal size of plots and the yields of the maize in kilograms on a school farm. Calculate the correlation coefficient R for the data and interpret your value in relation to the variables of the data. Now with this, if we are to use the conceptual formula, it will be very difficult. So we go by the easily calculation or calculation formula. And with this, the detail of the calculation is as summarized in the table. Now if you look at this formula, we are going to use the individual terms in this formula to construct the table above. That is what is used. So if you look at the formula, now if you come to the table, you can see that we have x, y, x squared, y squared, and xy. Now when you take them all, we will have the summary, that the totals of the individual column headings. Now substituting them into the formula, you end up getting 4 times 81. That's, in this case, n is 4. That's the number of pairs in the data set. Then the 81 is the sum of the product of xi, yi, as we had in the table above. Then minus 10 times 28. The 10 here is the sum of xi. Then the 28 is the sum of yi. All over the square root of the individual terms. The incorrect substitution, you end up getting 0.9648. Now what do you see? You see that the value of y here, the value of r here, that's the person's product movement correlation coefficient, is 0.9648. And you can see that 0.9648 is positive. And besides it being positive, it is very close to 1, which will give us a perfect positive correlation. And for that matter, it is interpreted as that's 0.9648 indicates a very strong positive correlation between the amount of fertilizer applied on the land and the yield of maize in kilograms obtained. Why? Hence, what it means is that the larger the amount of fertilizer applied on the farm, the larger the yield of maize you will harvest. Now there are some points to note. Here, the square of r gives the value of coefficient of determination. Now this term will be used under regression. And whenever you take the square root of the Pearson's movement correlation coefficient, you end up getting the coefficient of determination. I want you to go and try this example as given in the table below. And I read. The table below shows the time in minutes it took 10 pupils to solve mathematics questions when they were in primary 5 and when they were in primary 6. Calculate the correlation coefficient R for the data and interpret your results. So here we are using R as their time or their rate of calculation when they were in primary 5 and when they were in primary 6. And for that, when they were in primary 5, they had 11.1, 10.3, 12.0, 15.1, 13.7, 18.5, 17.3, 14.2, and so on. The same thing applies to when they were in primary 6. It started from 10.9, then it ended on 13.4. Now let's move on to other forms of correlation coefficients. Don't forget, from the beginning I told you that there are different types of correlation coefficients, and one of them is the Pearson's product movement correlation coefficient, R, that we've already dealt with. Now let's move on and deal with the second one, the other ones. Now for the other ones, we can talk of the Spearman's rank correlation coefficient, the phi correlation coefficient, the point Biserial correlation coefficient, and Biserial correlation coefficient. There's one thing you must note here. There are a lot of them. Just that under educational statistics, you will be limited to those that I've mentioned. And another point you must also note is that all these kinds of correlation coefficients have the same interpretation as that of the Pearson's product movement correlation coefficient. Only that the nature of the relationship between the variables determines the kind of correlation coefficient you should use. So first, let's deal with the Pearson's rank correlation coefficient. Now let's deal with the Pearson's rank correlation coefficient first. Now the Pearson's rank correlation coefficient is useful when the variables involved are all continuous and at the same time they are measured on the ordinal scale. In effect, it is useful when the variables involved are all continuous and can be ranked in ascending order. A typical example is that in our school situation is the ages of pupils and their marks obtained in a test. You can see that the age, when we talk of age age is a continuous variable. And also when you talk of marks, marks is also a continuous variable. And they can all be ranked in ascending order. Now, let's consider how to calculate or to deal with the Spearman's rank correlation coefficient. First, you arrange the values of each variable in ascending order. Then after that, you take the corresponding differences between, then after that you give them positions in the same ascending order. Then what will happen next is you take the differences between the positions, that's the ranks. Then with this, you end up using this formula, that's R sub S. Don't forget, the Spearman's rank correlation coefficient is denoted by R sub S. When you are talking of population, it will be rho sub S. Now, as I was saying, you then use this formula. With this formula, we say R sub S is equal to 1 minus six sigma d squared divided by n, then bracket open, n squared minus 1 bracket close. The d here is the differences between the corresponding ranks, and the n is the number of pairs of the variables or the values of the variables. Now there's one point you must note here. In the determination of the ranks, you must always, or if it happens that some of the values are tied up. When I say tied up, that is when you have one value appearing more than once in the data set. We say they are tied up. Ideally, they should have the same rank. But in this case, we don't do it that way. What you do is that you rank them as it should be. Then what you do next is you take the mean of their original rank positions. Then you assign them, or you assign the mean to them as such. Then another point you must also note is that when you take the sum of all the differences between the corresponding ranks, you must end up getting 0. So let's deal with it. I think the example, solving an example, will let you know the true nature of what we are talking about. So let's consider example. So let's consider the example below. The example below shows the marks obtained by 10 pupils in their mathematics and English exams in the table below. Now the mathematics marks are represented by the variable x. And the values or the marks of the pupils are as follows. That's in the corresponding row order. Then the marks obtained by the students in English is illustrated y, or is represented by the variable y. And the individual marks obtained by the 10 students are also in the row order. Now the question reads, determine the value of Spearman's rank correlation coefficient for these data. What does the value indicate? Solution. First thing you have to do here is you arrange the marks in ascending order and you assign the ranks to them as such. Now let's consider first the ranks of the marks, the ranks of the marks the students or the pupils obtained in mathematics. You see that 59 tied up 3 times. And if you are to arrange them, you end up getting 59 be in the 4th, 5th, and the 6th position. So what happens here is that we find the mean of the 3 ranks. And by that we will get 1/3 times 4 plus 5 plus 6 I take it again. You will get 1/3 times bracket open 4 plus 5 plus 6 bracket close. And you end up getting 15 divided by 3, which is 5. So what it means is that all the 59's values that appeared in the data set for mathematics will be assigned 5. So ranking as such, you will get 35, which is the lowest mark, up to 78, which is the highest mark obtained by the pupils in mathematics. So starting from 35, we have 1, 2, 3, 5, 5, 5, 7, 8, 9, 10. So you can see that one of the 59, which would have been of rank 4, has been substituted by the mean 5 of the ranks. Then the other also was substituted, that is the 6th rank, has been substituted by 5. Then the 7th rank, the 5th rank was substituted by 5, and the 6th rank was what? Substituted by 5. So you continue from the 7 to what? 10. That's the 10th one. Then when we come to the English, the ranking for the English, we have 55 tying up twice. So in this case, when you arrange them as such, we will get 55 falling in the position of 5 and 6. Now taking the mean of 5 and 6, we will get 5.5. So now with the rare ranking, for English, the lowest mark was 37 and the highest mark was what? 73. So we arrange them in that order. Then with the ranking, we start from 37 being the first position, 54 being in the 4th position, then 55, which should have been in the 5th position, has been substituted by the mean, which is 5.5. And another 55, which has also been in the 6th position, has also been substituted by 5.5. Then we continue from 7 to 10. Now the detail of this whole calculation is as shown in the table below. So you can see that by rank, we now take the reverse, that the highest one will come first on the table for the marks obtained in mathematics, that's XI. So we start from 78 down to 58. So if you look at the descent, if you look on the ranks, see that 78 was then in order of the raw data recorded. You can see that 78 tallied with 68. So recording that one too, you see that 68 will tally with what? 78 here. Then the rank for the 2, that's the rank for those or people who obtain 78 is 10. And the rank for 68 is 9. So when you take the differences between 10 and 9, you get 1. Then when you take the square of the differences, that's 1 squared, you get 1. Now let's come to the second situation, that's the ranking as the data, raw data was recorded. The second people had 59. Then that's for mathematics. Then in the ranking, it was 5th. 59 was 5th. Then the same people, that's the second people, scored 37 in English. And in the ranking for English, it was the first. That's 1. So taking the difference between 5 and 1, you get 4. Then 4 squared, you get 16. This is followed up to the last one. That's the 10th student in the case of the raw data recorded. For the 10th student, the 10th student scored 58 in mathematics. And it was ranked 3rd. And the 10th student, this same 10th student scored 52 in English. And 52 was ranked 4th. So subtracting 4 from 3, you get -1. Then -1 squared, you get 1 here. So as you can see, when you take the sum of all the differences between the ranks, you end up getting 0. Then you take the sum of the squares of the differences, you end up getting, that's sigma di squared, you end up getting 27.5. Now substituting these values, you can see that we had 10 pairs. So n is 10. Then d is 27.5. So substituting these values into the formula, it will be 1 minus 6 times 27.5 all divided by 10 bracket open 10 squared minus 1 bracket close. and you end up getting 0.833, which is positive. Of course, with this, there's no way you can get negative because of the square of the differences. Now, with the reinterpretation, Spearman's rank correlation coefficient being 0.833 indicates a positive correlation between the marks in mathematics and in English. Hence, people who tends to do well in mathematics will also do well in English because of their positive nature. Now I want you to go and try this question. The table below shows the ages in years of some peoples and the time in minutes they use to complete a class test. You go and solve this question. Try this question. Now let's move on to the second correlation coefficient. We call it phi. Now, as on the board, you can see say phi correlation coefficient, which is normally symbolized as, I don't know the symbol for the name, but this is the symbol for phi. It's the measure of the relationship between two binary natural dichotomies variables. When we say two binaries or natural dichotomies, it's a variable. When we say a variable, it's a natural dichotomy. It's a variable that naturally can have two main aspects or two main differences. Example, a typical example is age. Is a gender. A typical example is gender. When you talk of gender, we either have male or female. So you can see that it has two main types. Then you can talk of employment status. We have unemployed and employed persons. So I think this example is enough for you. Now one thing you must note is that with the phi correlation coefficient, all the variables are measured on the nominal scale. So if you take gender for instance, gender is measured on the nominal scale. When you talk of employment status, it is also measured on what? The nominal scale. As stated earlier, this phi correlation coefficient is also measured in the same way as the present product movement correlation coefficient. Now, before you can understand the formula used in calculating the phi correlation coefficient better, let's deal with an algebraic example. Let's say we have two variables x and y as in the table here. Then the two categories of y are coded 0 and 1, 1. The same thing applies to the two variables or the two categories of x. One is coded 0 and the other one is 1. Don't forget, if in reality we were to use this as gender, you will say this is what? Male. And the one is what? Female. Then the employment status, you will say this is what? Employed. And this is what? Unemployed. The one is unemployed. Now let's say if you take the number, the x, those who fall within the x value 0 in correspondence to the y value 0, we have A. Then when you do the same thing in that's for those who fall within 0 and those who fall within 1, you get B. The same thing applies to the second category. So now when you sum all, that's the one in the first row up, you get A plus B, then C plus D, then vertically, you also get A plus C, and then B plus D. Now with this leads us to the formula AD. AD means that's when you take the product of the main diagonals, that's A and D. Then you subtract the product of the off diagonal, that is B, C, and you divide by the square root of the product of the sum of all the entities as recorded in the row and as recorded in the column. You will get the entity phi correlation coefficient. Now the whole of this talks about what ends up in the lesson. Now this means that if you look at the formula, you see that whenever AD is greater than BC, you end up getting a positive value. But when AD is less than BC, you end up getting a negative value. So this leads us to the interpretation. This means that whenever the file compares the product of the diagonal cells to the product of the off diagonal cells, then what happens is that now to explain the formula further, this means that phi correlation coefficient compares the product of the diagonal cells to the product of the off diagonal cells. Now the denominator, which is this whole thing, is an adjustment that ensures that the phi correlation coefficient values from -1 to 1, as in the case of Pearson's correlation, Pearson product moment correlation coefficient. Also, this means that the two binary variables are considered positively related if most of the data falls along the diagonal cells. So that's what I mean by when AD is greater than BC. In contrast, when the two binary variables considered negative, when the two variables are considered negatively related, then the data that falls on the off diagonal are the most. So let's try an example. A random sample of 25 pupils in the Tano South district was made to undertake tests in a number of subjects so as to determine the effect of gender on academic performance, that's either pass or fail. The result is as shown in the table below. So that's the results, the summary of the whole result that is shown in the table below. Now the question is, find the 5 correlation coefficients for the data and interpret your results. So first, from the table, you can see that when you take the gender, that's the number of males who pass, there are 4. And the number of females who passed, there are 8. Then the number of males who failed, there are 9. Then the number of females who failed, there are 4. Now summing up the those who passed, we end up getting 12. Those who failed, we end up getting 13. And the number of females who passed or failed, they are 13. Sorry, the number of males who passed or failed, they are 13. And the number of females who passed or failed, they are 12. So it means when you come comparing this to the formula, A is 4, B is 9, C is 8, D is 4, meaning A plus B is 13, C plus D is 12, A plus C is 12, and B plus D is 13. Now substituting these values into the formula, we will get 4 times 4, all minus 9 times 8, all divided by the product, the square root of the product of the sums. That's the row sums and the column sums. And you end up getting negative 56 divided by the square root of 24,336, which will result negative 0.3589. Now, the phi correlation being equal to negative 0.3589 indicates a weak negative correlation between people's gender and academic performance. Hence, a weak negative relationship between people's gender and academic performance. What it simply means is that a people's gender can slightly affect his or her academic performance. What I'm trying to say is that the gender of a people does not affect the people's performance too much. Though it can affect it, but not all that serious. So I would like you to go and try this question. That's a survey on some people, on teachers. In a circuit was conducted to find out the impact of teachers' marital status, married or not married, on their attendance. That's punctual and not punctual to school. It was found that married teachers were punctual and not punctual on 109 and 66 occasions respectively, while non-married teachers were punctual on 120 occasions and not punctual on 85 occasions. The question is, calculate the 5 correlation coefficients and interpret your results. Now we move on to another correlation coefficient called point Biserial correlation coefficient. The point Biserial correlation coefficient is used to measure or determine the strength of the degree of the relationship between two variables, with one being continuous and measured on the ratio or interval scale, and the other being naturally dichotomous and measured on the nominal scale. Don't forget, any continuous variable can be measured on the ratio scale or the interval scale. And any variable which is of natural dichotomy can also be measured on the nominal scale. So in reality, if you take example, gender of pupils and their marks in mathematics. So you can see that the gender of pupils is a natural dichotomy, whilst the marks obtained by pupils in mathematics is continuous. Then you talk of the staff, that's teaching and non-teaching staff of a college of education and their monthly gross salaries. You can see that the monthly gross salary of teachers is what? Continuous. Whilst the staff being teaching or non-teaching is also a natural dichotomy. Don't forget, this one too use the same interpretation as this one too. That's the 5 correlation coefficient, also use the same interpretation as there's Pearson's product moment correlation. Now let's move on to Biserial correlation coefficient. This one deals with the case where we want to determine the relationship between two variables, of which one is continuous and the other is of artificial dichotomy. When I say artificial dichotomy, it's artificially. It is not of two categories, but by your own credentials, you divide it into two. Example, you talk of the age of pupils or the age of some people. We can classify them as adult and young. That's artificial dichotomy. You see, the age of pupils is naturally not of two dichotomies, but because we have decided to divide them by our own credentials, we say it is what? Artificial dichotomy. So example is the age, being young and adult, of pupils and their marks in mathematics. Of course, marks obtained by pupils in mathematics is a continuous variable. Then we can also talk of the monthly income. That's, naturally, monthly income of workers is not of two dichotomies. But by our own credentials, we can grade them as what? Or divide them into low and high. Into high and low, sorry. So if you talk of teachers, years, of working experience. Of course, years of working experience is a continuous variable. And when you compare to their income, which is of high and low category, you have it. And this one, the interpretation is the same as that of the Pearson's product movement correlation coefficient. So, my dear students, let's move on to all this hula baloo in correlation. What impact will it have in our education system? First, you can use correlation coefficient for selection and placement. That's that a people or a student who does maths in mathematics will be able to do well in physics and chemistry, and as such it will be convenient for the child to be placed in the science class. Then say it is used to determine the reliability of standardized and classroom tests. Now when we say reliability, it's the consistency of the existence of something or the occurrence of something. So if you know that a student does well in mathematics, you can boldly say that in the next test he or she is likely to do well, and as such the marks recorded in the second test will be say is consistent to that in the first test. They say it aids in the provision of evidence for the validity of assessment instruments. Now, when you want to assess students, you use a certain instrument and it measures all the capacities or capabilities of the pupils so far as the psychological thinking is concerned. When you talk of the assessment, we can also say that by this student, I can use this instrument to determine his or her level of performance, even though I couldn't use the first one. They say it puts teacher in the position to predict the future performance of a student. I think this goes with what I've already explained. If let's say you have a pupil or a student who is very good or he did well in the BEC results, you as a teacher, knowing the students, can always rely on the student past record to predict that student's performance in the SS level or at the SS level. They say it is useful for research purposes. Of course, this one is self-explanatory. Maybe you want to compare situations with situations. Which one is better, which one is worse. Thus, you want to conduct your research on these things, these situations. You can use correlation coefficient or correlation in doing that. So, my dear students, this brings us to the end of today's lesson. I hope you enjoyed it. And I also encourage you to continue working more examples. Good day.